All right, good afternoon, everybody, and welcome back to another live stream. Sincerest apologies that we ended up having to reschedule this one. I know we were supposed to do it last week. Part of it, honestly, was that I was still putting some polish on the stream, and I needed some extra time. But honestly, the other big reason, if I'm being completely honest, is I got a little bit busy with the Elden Ring DLC that came out last week. So I'm personally having a lot of fun with it. And I would consider myself not that great of an Elden Ring player. In fact, I personally have still not even beaten the main game. But I'm having to the people that are out on the internet that's saying it's too hard, yeah, it's hard for sure. Yeah, but I don't think it's necessarily harder than the base game. But anyway, you didn't come here for that. What we're going to be talking about today is Ragas. And so what is Ragas? So we are continuing along with our Summer of Rag series here. So in the first couple streams that we did, we generated a synthetic data set, and the synthetic data set contains fake knowledge items. So if you work in a large company or even a small company, perhaps, lots of companies maintain their knowledge for IT help desk support, things like that, in the form of knowledge items. And so what we did in our very first stream, which you might even call stream 0, if you will, was generating a synthetic data set around that we can play with for the series of streams. Then in the previous stream, we gave a very high-level introduction to what RAG is. So if you missed that, please go back and check those out. They're on YouTube, LinkedIn, or X, wherever I do my streaming. And so now, before that was just a very high-level introduction to RAG. We intend to go deeper in on the more complex RAG sort of optimizations. But the one thing that I wanted to pause before we get into that is determining how we want to do evaluation on our RAG pipeline. And the reason for this should be self-explanatory. It's simply that whenever we make our adjustments to the RAG pipeline, we want to evaluate how well those adjustments perform over time. And so that's why we are taking time to intentionally focus on this right now. Now, when it comes to traditional machine, let me think of how I want to phrase this. When it comes to traditional machine learning, whether it be a binary classifier or other sorts of regressors, things like that, all AI is finding patterns in data and then training a model at a snapshot in time to make an inference at a later point in time. And when I mean inference, I mean a very educated guess, but it is still ultimately not the inference is not perfect. It can deviate from what you would expect. So in traditional machine learning context, the way that we manage that with these binary classifiers and whatnot is calculating these metrics, things like the F1 score, precision, recall, ROC-AUC, or in regressors, we could calculate the root mean squared error, or even across both of those. If you want to check the stability of your data, you might do a population stability index or a Kolmogorov-Smirnov index, things like that. We in the traditional AI community, that is something that we are very concerned about because we want to ensure that our model is performing effectively over time. The challenge with deep learning models and then generative AI in particular is that you can't really do that. And the reason you can't really calculate those metrics is the reason it's called deep learning is because the parameters and the calculations and the metrics and whatnot are so deep that you just can't, they're effectively a black box at that point, and you can't do these typical mathematical calculations that we do in a typical, a traditional machine learning context. So how do we get around this? How do we manage through this? So this is where the Ragas framework enters, at least for the LLM RAG context. And so there is a positive and a negative side about what Ragas does. And it's not, I guess I should say, this is not localized specifically to Ragas. This is with all large language models. And that is, what Ragas does is it uses a large language model to assess the effectiveness of our RAG pipeline. Now, catch what I just said there. What I basically just said there is we are using one model to validate another model. That is a huge no-no. That is that. So in a traditional machine learning context where we are creating binary classifiers or regressors or whatever, we would never do that. We would say, no, we're going to calculate an F1 score. We're going to calculate ROC-AUC, something like that. Using a model to validate another model is very much turtles all the way down sorts of thing. You can do that forever. But the problem is what's the alternative? So the only other alternative is human evaluation, and we can argue back and forth of whether or not that is actually a valid form of validation, because humans have their own biases, they have their own opinions, they may answer these things incorrectly. Not to mention also the fact that it's time consuming. So if you imagine, you wanted to evaluate 100 different records of like RAG elements, a human doing that would take a long time, whereas a machine doing that would take effectively seconds or minutes or something far shorter than the humans. So what might make sense, to be clear, like I understand the concern around using models to evaluate other models. I also understand that we don't really have much of an option. So what I would actually recommend, at least for the short term, until like these models start to get better and better, we can rely on them more, is maybe you want to do a hybrid approach. Maybe you want to have what was I going to say? Sorry, I just got a text and I got completely derailed there. Oh my gosh, I totally lost my train of thought there. So what were we just talking about? If anybody's in the chat and can help me out. Oh my gosh, I've never blanked like this hard on something like this. Anyway, so the hybrid approach. Yeah. So the hybrid approach would be like if you wanted to, have at least a subset of the RAG things that you want to evaluate done by a human, where you might use a Ragas a framework like Ragas to do a more programmatic evaluation. Okay. So the way that Ragas works is that it evaluates things at multiple different levels. And in order to use Ragas, we obviously need to have data to support that. So this is going to be part one of the stream. So part one of the stream is, so we synthesized our knowledge items, but what we don't have is, like, imagine that we're already out in production and we've already got users asking questions, and the questions are being generated, like the AI responses are being generated per the context. And then maybe even after the fact, you might have some ground truth that says, yes, this is actually what happened. This is the sort of data that we need in order to be able to play around with Ragas. So in a real world context, you just go out and grab your logs and then you just do all these calculations on your logs. But in our stream, we're going to have to synthesize our own data set. So I'm going to go ahead and start sharing my screen here, and let's talk about the synthesis. So I've been as you kind of have seen in the recent streams, I've been doing all my work on Kaggle recently, and that's partially because I can do it anywhere. Like actually, 80% of today's stream I did directly on my Vision Pro, and then the other 20% I did on yes, thank you. I forgot. Yeah, the other 20% was done on my iPad. So I actually did none of this work today on my actual MacBook itself. And in fact, the only reason I have a MacBook at this point still is because I can't do streaming and I can't do a few other things without my MacBook. Otherwise, I could totally get by with my iPad, and I love my iPad over here. But anyway, what was I saying? Yeah, so generating this test data set. So Ragas actually does have a framework for generating the test data set. I guess so. This is a new notebook. I did a couple things to go ahead and get me going because last time I know this was a little bit of a hang up in the last stream where the pip installs took forever. So we will cover what all this code is doing. But just to say, the code that you're looking at right now is nothing new. This is all stuff that we've worked with even just in the last stream. And we're going to continue working with this stuff here. So, so let's talk about how Ragas does its data set synthesization, because it honestly was a little bit confusing the first time I saw it. So this is the actual Ragas website, and this is the diagram that they demonstrate for how they synthesize questions. So the first concept that I want to point out here is that Ragas operates the data set synthesization, I should say, operates on this idea referred to as an evolution. And what an evolution means is that you can have, it's trying to come up with multiple different sorts of synthesized data set rows so that they're not all just the same. So what do I mean by that? So you can see kind of here down here is we always start with a basic question, but then we might evolve it out to be more of a reasoning question. So this fork over here is where we might have tell the Ragas framework to produce a question that requires some reasoning logic around it. And then we might have conditioning going on here. So if we want to ensure that the question over here requires that a specific condition is met, then the evolution will ensure that the question answers that. And then finally, we have the multi-context down here, and that is we are basically saying, okay, based off of how we're generating the question, let's make sure that we are including multiple pieces of context here. All right, so that's the core idea of the revolution there. So I'm sorry, not revolution, evolution. So let's come back up here and talk about what's going on up here. All right, so Ragas, the way it simulates its data, it actually uses 2 large language models. And technically speaking, you don't have to use 2. You can use the same. In fact, I'm going to be using the same because I don't see a purpose in using 2, or at least for our testing purposes, I should say. But the 2 large language models are a generator LLM and a critic LLM. And so basically, and we'll walk through this picture here, but the generator LLM, its responsibility is basically coming up with the questions or evolving it into the reasoning things and the conditioning things or whatever. And while the critic LLM is basically looking at the outputs and as the name implies, it's being a critic on whatever the LLM generates. So basically, if the generator LLM produces something and then the critic LLM comes along and says, that's crap. So then we do this retry thing, and then we kind of just do this repurposing thing. So let's walk through this flow here to talk about how it goes about this. So the first thing that it does is it takes our corpus of documents. So again, we already generated. We did this in the last stream. We already have our KI docs here loaded up as such. So let's go ahead and look at those really quick. So you can see we have all of our knowledge items in here represented as these lang chain document types. And so if we come back into here, that the first thing that it does is it will basically create a vector store on the fly for you. And when I mean a vector store on the fly, I mean so in the previous stream, I demonstrated how we could use Chroma as like an in-memory vector database. It's doing something similar to that, but it's creating these nodes, like these individual nodes that would represent like a document chunk. So one little gotcha here to be mindful of, and we're not going to necessarily care too much for this stream, but when it does this particular portion of creating the vector store for you, it does its own arbitrary chunking. And I think it's like 400 token chunks of documents, which means that if you want to use the Ragas simulation framework going forward, like let's say you have a different chunking strategy, you're going to need to ensure that you are somehow like customizing it to where you can use this simulation framework to also include that custom chunking functionality. And to be completely transparent, I don't know how to do that right now, just because I've just been doing the basic stuff, but I do know it's possible. So it is possible to do that chunking. And again, we're not concerned with that for this stream because we'll cover that in a different stream, like optimizations for chunking. But in this stream, we're just going to say we're okay with whatever its arbitrary thing is doing. All right. So anytime you see a red diamond like this is the effectively. Well, no, I'm not going to say what I just, because I'm rereading this and now I'm changing my mind. All right, so anyway, let's just move on to the red diamond here. So the red diamond here is basically, okay, step 1 is for however many test entries you want. So let's say we want a test, a data set that has 10 test entries. Then what it does is it will grab 10 random nodes from like this vector store. Now, let's say you only have, let's say you want to generate 50 questions, but you only have 10 nodes in here, then it's just going to keep randomly grabbing from this node set, and it will apply a weighting each time that it grabs one of those nodes to make sure that it's not grabbing the same node over and over and over. And so after we've collected those random assortment of nodes that we want to go through, let's say we just want to pull out one of these nodes. And again, a node in this specific context that we're talking about here would represent that document chunk from basically one part of the knowledge item. And so then the first question here, it goes directly to the critic LLM actually. And so what the critic LLM is actually doing here is it's looking at that document node, and determining, is this a good candidate to be actually trying to simulate around? So basically, like if it were to find like a document node that was, I don't know, like 2 words long or something like that, like trying to formulate a question, a simulated question and a simulated answer like that around that is just not conducive. So if it determines that the node is not conducive for this sort of thing, then it just goes back and looks for another random node. But let's move on. So let's say like it determines that this particular node is good or this chunk is good. So then it moves on to generating the seed question. And so one thing I do want to call out here is it calls it the seed question, but actually whenever you look at how to implement this in code, it refers to these seed questions as simple questions. And so you can actually say, like for the most part, if you are okay with this seed question, and you can even see it represented as such here, then we just go on to the no path, and then we just generate the answer based off of the seed question, and then just move on. But in other cases, like I mentioned, so this is where the evolutions come in. So let's say we want some reasoning questions, we want some conditional questions, we want some multi-context questions. Then it goes down the evolution path with these new forms of prompt engineering to produce the evolved question. And again, just as you would expect, whether it be just the simple seed question or the evolved question, it is the critic LLM that is once again coming back and doing that assessment to determine, okay, is this a quality question? Is this a quality question that makes sense per the chunk that was provided? And then after that question has been successfully validated, then we produce the AI response that would be formulated around this question, and with the generator LLM. And then finally, once again, you can just imagine every time the generator LLM comes along, the critic LLM also comes along and determines the quality of the generator LLM's output. And then we finally produce our samples. And so I know I said a lot there. So one thing I do want to call out is I do have this completed notebook over here, and I do actually intend on writing a full blog post around this. And you can see like these are all my markdown notes on how the test set is generated. So it goes into more specifics here, and you know, for better or worse, the Ragas documentation is good at explaining concepts, but it's not really good at explaining like the details on how it got there. But like the source code for Ragas is actually, in my opinion, very readable, and that's because it's largely repeatable. So I actually just went into GitHub and looked at the source code and derived all this information myself. I know, I'm a nerd. Okay, so let's demonstrate how we would actually maybe synthesize a data set. Now, the one thing I will say here is within the stream, because we like, so let's just looking at this page here, how many LLM calls is this? It's 1, 2, we'll just stick with the happy path. 1, 2, 3, 4, 5, at least 5. At least 5, with a potential of more depending on the evolution, or if the critic LLM says the generator LLM needs to do a better job. So this can get literally very expensive, like very quickly. And that is another thing that you're going to want to keep in mind here. And something that I did within this notebook is for every other metric that we're going to calculate, I actually did note how many API calls is it. So like for this one here, this context recall, it's 1 API call. But for some of these, there's one on here that gets as high as 4 API calls, and that's per metric. So and so you can imagine that if you were to go and calculate all these different metrics here, that you're making a lot of LLM calls. So to the person that's asking the question in the chat, do you plan on sharing the notebook/code? Yes, it's already out there. So it's in my personal GitHub. So github.com/DKHunley. You're welcome to find it there under the LLM RAG guide repo, or here on Kaggle. So so I see the question came from YouTube. So let me go ahead and just pop this in for you on YouTube. So in the chat there, I just popped in the link. That is the precise notebook I'm looking at right now. And again, like I said, I'm going to be writing a whole blog post around this entire thing as well. But anyway, so let's come back to our other notebook here. So all we've done so far is we've just done imports and then setting up things like API keys, nothing particularly fancy here. And then we loaded up our synthetic data set, and then we loaded up our KI documents. So the first thing that we need to do, is we need to instantiate our critic and LLM, the critic and generator LLMs. Now, like I said, I personally in this particular case, do not care that they're the same. So I'm just going to call this chat model. Chat model equals OpenAI, or chat OpenAI. So this is just LangChain model, or is that right? Model equals GPT-4o. Is that right? Okay, that's correct. And so then the way that we actually manifest this, I guess we do need to pass in embeddings as well. So embedding, or set up the embeddings algorithm. So embeddings equals, looking at my notes here, OpenAI embeddings. Okay. All right, so we've set up the embeddings. Now I want to show a couple of imports that we needed to do here specifically for this test set generation. So you can see here these two lines that I've highlighted. These are the lines that we use for the test set generator. So you'll notice here that we have just a simple test set generator object. Pretty self-explanatory. This is the thing that's going to be doing the generation. And then you'll notice here within the evolutions that this is how we will actually indicate the distribution of how many of these things that we actually want. Now, because this can take a while, we're only going to produce one record, and so I'm just going to keep it simple by making it just a simple question. Pun not intended there, I guess. Keeping it simple with simple. And so the way that we can set this up, so let's go ahead and set up our test set. So our test set generator. So test set generator equals test set generator dot from LangChain, and then we need to pass in a couple of parameters. So we're going to pass in the generator LLM equals chat model. And again, like I said, I don't care that the generator and critic LLMs are the same here, so I'm going to make this also be the same object. So the question in the chat about wouldn't this work be more convenient in VS Code? Yeah, if iPad had a VS Code. I know, I'm a weird coder. Like most people don't code on an iPad like myself, and if I were exclusively a MacBook coder, which I am at work, like my work computer is just like a MacBook, I do exclusively use VS Code. So the only reason I'm using web notebooks is because if I want to use my iPad over here or my Vision Pro, what am I gonna do? I got to use these Kaggle notebooks, and plus the nice thing about the Kaggle notebooks is you can fork these off, and then anybody can do anything that they want with them. So yeah, that's why I'm doing what I'm doing. All right. So anyway, need to pass in the embeddings as well. Embeddings equals embeddings. But you're right. In a production context, you would never even want to work in a Jupyter notebook like this. It's just handy to work in a Jupyter notebook because I can annotate things crazy. Yeah. So no, right now I am streaming off of my Mac. So I do have a MacBook. Like I said, I'm super weird, but I prefer to do most of my work on an iPad. So yes, we are on a MacBook right now, but all this work was done on an iPad or with a Vision Pro. I'm a weird guy. So, all right. So that is instantiating the test set generator object. So, all right. So test set generator. Now that's just instantiating the object itself. It's not actually generating the data set itself. So the way that we create the data set is just using this test set generator. Test set generator equals dot generate with LangChain docs. So again, we have all of our stuff in LangChain here. All right, so we need to set our documents. So our documents are going to be our KI docs. Our test size, like I said, we are only going to produce one item this time just because it takes some time. And I already did do a load in of the 10 records that I did from another time, and that's what we'll be reviewing later on in the stream. But I just wanted to demonstrate this for now to see to show this works. So like I mentioned though, so if you wanted to get your own distribution of questions, what you would do is you'd create this dictionary of simple would be maybe half of them you want as simple, and then maybe reasoning you want, I don't know, 0.2, etc. And basically all these numbers need to add to 1. But like I said, I'm only creating one record for this, and I only care if it's simple, so I'm just going to set this distribution to equal 1. And then finally, I am going to turn this into a data frame just so we can show the output of what this looks like. Test set dot to pandas. All right, so hopefully that won't take too. Oh, commas. Commas might help. Distribution. Did I not spell that right? Distributions. Okay, I need an S there. My bad. All right, so this is going to take... Oh, I forgot it's got to embed the whole thing. So this actually might take a little bit longer. All right, well, let's just wait here a second. I mean, it shouldn't be too terribly bad. Yeah, so I'm reading the comments on the chat about like working in VS Code versus Notebook. So, yeah, like don't I guess don't worry too much about like the compute environment that I'm working in. I will say in a typical environment, yeah, like I do prefer working on a MacBook computer. I would like MacBook or Linux. I wouldn't mind either. It's just that like, and there's nothing wrong with Windows. Like you can get by with Windows. It's just that like the MacBook and Linux, MacBook is built on top of Linux and thus uses all the same Bash and ZSH commands. So it's preferable from a coding perspective to work on something like a MacBook. But again, I just love the form factor of an iPad. and I'm like one of the only people that I know that works this way. But even so, like it can be a very frustrating experience. Like when I did the whole MLX series, like I obviously needed my MacBook for that. I couldn't do that on the iPad. So I'm in this weird like I keep praying that like Apple would come up with like this hybrid computer, just like a Microsoft Surface, like where it's a true computer with Mac OS with the touchscreen, but they just don't, like, because they want my money, and they're doing a good job of getting it. All right, so this should be here, done here very shortly. I forgot that it has to do this whole thing. I thought this would be quick just with one of these things. I'm going to take a sip of my drink while we're waiting. All right, so the embeddings are done. Now it's going to do the one generation, which shouldn't take too terribly long. But now, I hope you're kind of seeing like why I'm going to be referencing material that I already used instead of trying to do everything from scratch, because it just takes too long otherwise. Okay, it looks like it just finished. All right, so let's go ahead and look at what was generated here. Okay, so here is the test set. Let's go ahead and look at the rows, and then we'll look at the individual pieces. So let's go ahead and look at the individual columns. So what we have here, so the context here, this represents one of the individual nodes. So this would have been like I said. So our knowledge items would have been chunked down into 400 token chunks, and so it would have randomly grabbed this one token. So here, I'm just going to go ahead down here and test set iloc 0, and then let's just look at the contexts. Okay, so you can see here, this is the specific chunk that I pulled out of one of my simulated documents. And so, you know, obviously the critical LLM determined that, yes, this was a good thing to build a question around. So let's go ahead and look at like what this question that it built is. So the question that it asks is, how do you test the connection to the company issued database after establishing it? That is such a generic question. At least most companies I know, you're going to have more than one database. But anyway, that's neither here nor there. Now, the one thing that's a little bit irritating to me, and not, well, I guess not irritating, but like that we need to address here is, so when we calculate all these metrics, we need 4 pieces of information. We need the user's original question, which we've demonstrated here is simulated. We need the context that we retrieved. So this is the context from like our vector store. We need the AI generated answer, and we need the after the fact ground truth. Now, do you notice something is missing here? Do you notice what is missing? The answer is that well, you can call it, in this case, because we're simulating it, you could say this is either the ground truth or the AI answer, but you'll notice there's not both. So if we want, and so this is a little bit of a flaw with the Ragas framework. However, I will say, like, I was going into their GitHub issues and was noticing, like, they are working on a version 3 of, I guess this is version 2 of their test set generator, and they are currently working on a completely overhauled version with version 3. So I would imagine that hopefully that version 3 will rectify the issue, but that means that we are going to have to take an extra step to actually generate the ground truth here. So I'm actually going to rename this. So I'm going to call this df test set rename columns equals. So I'm going to rename the ground truth column truth to answer, and then in place equals true. Place equals true. And so all this is doing, oops, I didn't put that in quotes, did I? My apologies. All right, so let's look at this again now. All right, so basically, like, all I did was change the answer. So now we need to generate the ground truth column. So what I'm going to do here is to try. The problem here is when I tried to generate the ground truth using GPT-4o again, it produced basically the exact same answer. So what I am actually going to recommend to do is I'm going to use my Perplexity subscription and call one of the llama models. So I'm going to call this llama model equals. All right, hold on. Llama model. I'm just going to copy and paste some of this. Oh, I'm going to copy and paste all this. Yeah, because we have to do a prompt engineering and everything. Shoot, I forgot about that. Yeah, no wonder this took me so long. Because I actually did get help writing this prompt engineering from a different model. But yeah, well, I'll go ahead and get rid of that. All right, so this is the ground truth simulation. So I had actually Anthropic's Claude 3.5 Sonnet actually generate this for me. Look at me. I'm using 3 different models in this stream. Claude 3.5 Sonnet, GPT-4o, and Llama 3 70B. All right, so yeah, I use it to generate this context or this prompt here. So I'm just going to do some copy and pasting here just to save on time. So what I'm going to do here, because none of this is new particularly, especially if you've been around and followed some of these other streams, but just walking through this really quickly here. Basically what I'm doing is setting this prompt within a link chain, using my Perplexity API subscription and setting the model as such. And then I needed to create a custom function that would actually create this ground truth. So I'm, again, just copying and pasting for time's sake, because I see that we're already 30 minutes in and we got a lot of material yet to cover. So just really quick, what is this doing? It's basically, as I note here from the prompt engineering, that we want to create a ground truth around the question and the context. So we need to grab the question and the context from the individual row, and then we need to simulate that ground truth if it's not already been created. All right. So the way that we do that here, I actually need to create an empty column. df test set ground truth equals blank, so we'll just create an empty column around that. So now let's just look at this really quick. All right, so now we have our empty ground truth, and then let's go ahead and let's pass this thing in. So let's call this, all right, so df test set ground truth equals df test set dot apply. We're going to pass in that function that we just created from above, and then we are going to do axis equals 1. All right, so that should go relatively quickly. Oh yeah, it's already done. All right. Okay, so let me .iloc. Okay, so this is the ground truth that it just generated. Obviously, this is not a real ground truth. And I guess one thing to note as we get further on is if you want to calculate every single Ragas metric, excuse me, you need all 4 of these pieces of information. So question, context, answer, ground truth. But if you only have like 3 or like a few of those metrics, you still can calculate some Ragas metrics. You just won't be able to do all of them. And we'll talk about those as we get to them. So now, all right, so now we have our test data set. Now, one thing I do, a couple things I want to call out for, here, let me just go ahead and show this again, set. So the columns here. So the only things that we need to keep here are the question, context, answer, and ground truth. We do not care about the metadata. And that's just showing the metadata that was associated to the context, and it's just showing the KI topic. We don't care about the evolution type. And just to call this out, because like this confused the heck out of me, and I still have no idea why they did it. Like, in fact, I'll go ahead and show you. I know this code so well. It's almost sad because I've spent so much time in it recently. All right, so if we go to the test set generator, and we go to the generator, and so if you look here, you might be wondering, what does that episode done mean? Well, this is the toRecords function. So it's basically taking our data, putting it in a data dict, and adding this episode done arbitrarily. This is just an arbitrary add here. It has no value add. I don't understand why this is here. So all that to say, just ignore this. I have no idea why they put that there. I don't know. Maybe they have a reason, but like I said, going into the source code, there is no like, and if you do like a control F throughout this entire thing, not just on this page, but throughout the entire repo, you won't find this referenced elsewhere. So this boggles my mind why it does this. Okay, so unfortunately, we're not quite ready to calculate the metrics yet. A lot of this is just prep toward calculating the metrics. But I guess the good news is you'll find that actually calculating the metrics themselves is very easy. All right, so the next thing is by default we are not ready. This is not ready to be passed into like the Ragas framework yet, because specifically the Ragas framework wants things in the format of like a Hugging Face data set, and like it's kind of particular. So I'm going to do a little bit of copying and pasting here. I created a custom function to help get around this. So I called this pandas to Ragas, and so basically what it's doing here is the first thing you need to do is ensure that like all your null values are filled appropriately. So we have our text columns, question, ground truth, and answer. We need to make sure those are not null, and then we need to make sure that each of our contexts is like formatted in this list type, and then we convert it to a data dictionary, and then we pass it in through the Hugging Face thing. Part of the reason I'm blowing through that really quick is because that's not really important. This is not like it's important in the sense that like you need it to calculate the metrics, but this by itself doesn't really do anything for us other than it's just a reformatting of the data. Okay, so I'm gonna call this Ragas test set, and I'm gonna pass on our data set. So just a little copying and pasting in here, and so now our Ragas test set, as such, is ready to go. So you can see here we have our one row, and we have all this stuff. Now, actually calculating the metrics is extremely easy. So let's go back up to our imports here, and just to show you what our imports here, we're going to cover these in depth, but we're basically going to be making use of this line. In fact, let me just, to make it really easy, let me move this down. We're going to be making use of these 3 lines right here. And again, we will talk about what each of these is calculating here in a little bit, but basically we have our primary evaluate function, and then we just pass in each metric that we want to calculate. And we don't necessarily need to calculate all of them. Now we will be just to, and we'll talk about what each of these metrics is doing. But when we actually come on down, so let's go ahead and come on down and show how to write this code. So I'm going to call this Ragas scores equals, so like I mentioned, we have that evaluate function up there. So we need to pass in the data set equals Ragas test set. Then we need to pass in a model. So I'm going to use for this model. Actually, you know what? I am going to use GPT-4o here because it does not matter. But I'm gonna talk about a little gotcha that I ran into here in a second. And then we need to pass in all the metrics that we want to calculate. And simply what we want to do there is just just a list of all these things. And so while I'm talking here, I'm coming in and pasting this in from below. And so these are all the metrics that we want to calculate. And that is the code. Like that is all the code that you need to actually calculate all these metrics. So from that perspective, very easy. And for better or worse, though, if you come into this documentation and want to read up on all these different metrics and what they do, I personally think it's a little bit confusing. Like a lot, because a lot of this is abstracted away in the content, meaning that like it doesn't really reveal how these metrics are being calculated under the hood, not through the documentation at least. But like I said, I went through all the source code here, and so and I personally find it relatively easy to work through these things. So actually, all the metrics are in this metric folder. So like if you want to look at like the metric, this faithfulness metrics here, all of them have like, so you have your like base class here. All of them are initiated through this a score function here. So if you ever want to go and figure out, read the source code for these, go into the individual metric, go look for the a score function, and just kind of read through it, and you can very kind of quickly discern for yourself like what's going on. And I'll be talking about this for each of the individual metrics. But anyway, let's go ahead and run this for at least our first one here. Now, while it's running this, because this will take a minute, the gotcha that I ran into is I tried doing this against 10 different so I simulated 10 records, and I wanted to evaluate the 10 records with GPT-4o specifically. So what's going on behind the scenes is it's doing this async processing where it's basically having all these run in parallel. And the problem with that is I hit rate limits really quickly. Is like, so I was hit like because we're doing so many API calls here, I started to get rate limited very quickly. So I actually, in order to produce all of these metrics for all 10 records, I had to turn this down to GPT 3.5 Turbo, because GPT 3.5 Turbo is more forgiving on the rate limiting. But that's why we're okay here with GPT-4o, because we were just doing it for one record. But that is one major gotcha you're going to want to watch out for. And there are ways to curb around that. There's there might be a retry back off sort of thing that you can do, or you can chunk these down and, knock out half these metrics, or only calculate the ones that you need to, or maybe just calculate on a subset of the data. But that is something you want to be very careful of. And like I said, there are so many API calls going on in here that it gets relatively expensive relatively quickly. So let's go ahead and, so we just generated the data set. I'm going to turn this into a data frame. df ragas scores equals pd, or equals ragas scores dot two pandas. Ragas scores. Okay, and so what you're going to see is you're going to see the question, context, answer, ground truth. So this is nothing new. And then you're going to see all of our scores here. And we'll come back to this one, but I'm actually going to jump back into my other notebook because my other notebook actually has more records. And because this is all the code we're going to run today. Like everything else from the stream the rest of the stream is just going to be me talking about the conceptual, like what is this thing doing sort of thing. So that is actually the end of the code. So let's jump back into our other notebook here, and like I said, we're gonna just pick up where I left off here, where I generated like 10 records here. So yeah, so let's talk about the different metrics first. So like I would say there's 3 categories of metrics within Ragas. You have what are referred to as the component-wise evaluation metrics. So these are looking at like some of the individual components of like the different contexts. So like comparing the ground truth to the AI answer, for example. And so some of these metrics, like these component-wise metrics, these are the metrics where, like, let's say you don't have the ground truth, or you don't have the context for whatever reason, like you're missing some piece of data. You can still calculate some of these metrics. You just won't be able to calculate all of them. Now that brings us into the end-to-end evaluation metrics. So as the name implies here, like this is actually doing like an assessment on like the full end-to-end RAG pipeline. And for these metrics, you generally do need like the full set of data. And then finally, we have what I refer to as the aspect critique metrics. And so these aspect critiques are these are things that the model is looking for to. Well, we'll get to it when we get to it, because I'm like it'll be easier to demonstrate when we actually get down there. So first one on here is the faithfulness score. So the faithfulness score, what it's trying to do is trying to see how factually consistent is the AI answer compared to the context. And so the way, and you can see here, and so this is like latex that I got from the actual documentation. And this is the part that confused me. It's like, well, number of claims in the generated answer that can be inferred from the given context versus the total number of claims in the generated answer. So what does that mean? What that actually means, and I went through the source code here, is the first thing that it does is it asks the large language model to produce a number of simpler sentences based off of each individual sentence in the AI answer. And then it takes each of those individual each of those simpler sentences from the AI answer and determines if that simpler sentence is actually relevant to the actual final answer. And so that's how this score is calculated in the end, is that we take all the statements that we determined that are faithful to the context over the total number of claims in general. All right, so number of API calls here. So we have the one LLM call to generate the simpler sentences, and then we have another LLM call that's going to judge the faithfulness of the simpler sentences to that context. So in order to derive this, you are going to need the original question / query, context, and the AI generated answer, but you do not necessarily need the ground truth here. So this is another data set down here that this is what I was talking about, where I generated the 10. So you can see here that we've got all these answers here, these contexts and stuff here. Now the one that it's a little bit of a false flag here. So if in the synthesization process, it's possible that the Ragas framework kind of screws up, and then it'll produce a null value. So the fact that we're getting a faithfulness score of 1.0 here is a little bit concerning, given that our answer is a null. So how can the context be faithful to the answer if the answer is nothing? So that's a little bit of a false flag there. And again, that kind of just illustrates the idea that using a model to assess another model is not the best idea. But again, what else are you going to do? We don't have the other option of calculating that F1 score or whatever for these these RAG evaluation things. Excuse me. All right, so now you can see this one here. This one's kind of interesting. I'm actually curious to drill down on this one further. So let's all right, so I'm curious to, I'm going to paste this down here. .iloc. Which row is this? Row 3. Okay, so row 3. I want to look at the question. No, I want to look at the context. That's right. Okay, never mind. I don't want to look at this because this is going to take too. this if we went and evaluated why each of these were generated, we'd be here all day. So, but yeah, if you were to just go through and read this notebook, you'd be able to determine how faithful these things are or whatnot. So obviously the most ideal score is a 1.0, whereas a 0.0 would be the least ideal. And you'll see for the most part, we do get a 1.0. Now again, we get this weird false flag with the NaN value there, but it is what it is. All right, so that's faithfulness. That is how the first one is calculated. And again, that's why I wanted to talk about, because the documentation doesn't talk about anything about these simpler sentences generation things. So that's why, and going through that source code, while a bit of a slog, was definitely useful in the end. All right, so let's move on to the next one, answer relevancy. So this is basically taking the AI answer and trying to determine how relevant it is to the question itself. And so the way that this is calculated is a little bit interesting. So what we're actually going to do, and so I describe in the steps here. So the first thing that we do is we take the AI answer and we actually generate a brand new question on that. And then maybe the reason that we do that is Well, we actually generate the question for the next step. My apologies. But immediately during that same call, the other thing that we ask is to check if the AI answer that we've submitted is non-committal. And what I mean by non-committal is it answering the question as I don't know, I'm not sure, things like that. So that's what non-committal would be. And so then the LLM is prompted to say if it is a non-committal score, give it a score of 1. If it is a non-committal score, or a committal score, if you will, then give it a 0. And so the next step after that, so we get the generated question, the committal score or the non-committal score out of that. Then we take that generated question and the original question, and then we embed them using an embedding algorithm. And then after we embed those things, we calculate the cosine similarity score between the embeddings, and then we multiply the committal score by the cosine similarity, which again, the documentation is incomplete here, because if you look at this latex that I grabbed out from here, it does demonstrate how the cosine similarity is calculated, but it doesn't mention anything about this committal score thing. But I assure you it's there. Like, let's go look. Like, so the answer relevance. So yeah, this is what I'm talking about. So like the nice thing about this repo is they structure, like, almost all the prompts are toward the top. So you can see here, like, the first prompt here is generate a question and answer, and identify the answer if the answer is non-committal. And then if you continue to go down through the code, where is it at? So this score here, you can see that the final score is derived by calculating the non-committal scores to the cosine similarity. So again, the documentation is a little bit lacking right here, but it's all right. We got through it. So yeah, so we have 3 API calls here. We have one LLM call to generate the question and the non-committal score. That's done in one call. And then we have each of the individual embedding calls to embed the generated question and then embed the original question. And the only data that we need here is the retrieved context and the AI generated answer to produce the final answer. And so this is going to end up producing a score between 0 and 1. So 1 would be obviously the answer is very relevant given the context, whereas something that's lower would not be. So all these are pretty spot on. Now the one that's obviously a little bit tricky here is the one that's a null value here. Again, a bit of a false flag here. And in fact, you might even just throw these out so they're not screwing up your scoring overall, like anything with null values. But I would say, generally speaking, these seem right. Like, I don't see any cause for concern of why this answer relevancy would not be correct or not. So yeah, so that is that score. All right, moving along. And again, we're moving on along a clip here just because, like, we still got a lot of material to cover. So let's talk about context recall. So if you, for those of you who already work in the machine learning space, context recall is very similar to the recall that we know from general statistics. So recall in general statistics is basically trying to determine, based off of the ground truth, like how often were we correct. And so the way that I like to remember precision versus recall, and we'll come across precision here in a minute, so it's important to keep this in mind. So, like, imagine, like, we would want a machine learning, like, let's say I'm building a machine learning detector that detects intruders around a building, like using a camera. So, like, if a camera sees, like, somebody trying to get in the door, like some door, you would want to have a high precision there, because you would want the model to you would want somebody to take action even if there was not action needed to be taken. So, like, if the model got tripped in this scenario, you would want, like, a security guard going and asking this person, hey, what are you doing? And it may be the person that, I got lost, or, I got locked out, whatever. It may be a totally benign scenario, or it may be an actual intruder trying to break in. So in that scenario, you'd want something that's really high precision. On the flip side, like, let's say you were using some machine learning model to diagnose cancer. You don't want like the model just willy-nilly telling everybody that they have cancer. You want it to have a very high recall. A high recall in the sense that you don't want the model just tripping off of anything, tripping is not the best word, but like being in what's the word? Like, you wouldn't want the model just saying, like, everybody's got cancer. You only want it to say, yes, we think it has cancer if this person really does have cancer. So that's where you would want a really high recall score. So anyway, so that's with that context in mind. So the context recall then is just determining the number of sentences that in the ground truth that can be attributed to the actual context itself. So that's what this latex score is representing here. And so the way that we do that is we iterate through each of the individual sentences from the ground truth and see if they can be properly attributed to the full context at large. And so if it can be, then it gets a score of 1. If it can't be, then it gets a score of 0. And so the final score is derived by taking the total number of scores, the ground truth sentences that can be attributed to the context, divided by the total number of sentences in the ground truth. So this is just one LLM call. The one LLM call is just taking each individual sentence from the ground truth and determining if it could be appropriated to the context. Now, the one odd thing in my mind, and I don't know if this is a mistake or not, is you'll notice that technically speaking, in my opinion, the only things you need are the retrieved context and the after the fact ground truth. But for some reason, the way that the code manifests, you also do need to pass in the question, because if you don't pass in the question, then you will have a coding syntax error, and I don't understand why. Like in my opinion, this is not required, but that's just a minor quirk of this process, or the Ragas process here, but not a huge concern. I mean, you're probably going to have this. I can't imagine a scenario where you'd have all the this whole row, like all this information here. Like the only piece of information I can understand that you wouldn't have is probably the ground truth of all of these. Like I can't imagine a scenario where you'd have the context and the answer, but not the original question. So it's not a big deal. So just looking at the context recall here, so you can see here that we have a lot of good. We want to have that score of 1, of course. I am kind of curious why this one was not as good, but I'm not going to look too deep into that, but you might want to. Again, all these different metrics are really going to be dependent on like what concerns you the most. So if you are building a large language model and you want to ensure that it's getting it, like back to that whole cancer scenario, like if you want to ensure that the language model is correct, and not necessarily being willy-nilly with its answers, you want to have a high context recall score for sure. All right, so let's talk about the flip side then, the context precision. So we talked a little bit about the precision, and again, the reminder of the scenario that I like to remember with precision is like if you're trying to build an intruder detection model, it doesn't matter if the person, like you want a security guard going in and checking for the intruder, like a potential intruder, even if it ends up being a false positive. So that's what the precision here is kind of doing. The calculation for it is a little bit confusing, so I broke it down here step by step. So the first thing that it does is it takes the question AI answer and context to determine how helpful the context is, and then the LLM gives a verdict of 0, 1, where 1 indicates that the context is helpful, whereas 0 is not, and then and then as part of step, then in order to calculate the final score here as represented by the latex, the denominator is going to be the total number of the total number of verdicts in the item, whereas the numerator here is going to be the number of true positives. But the way it's calculated is kind of interesting. It's done at like each individual time step, like not time step, but each individual piece of whatever that's passed in. And like I guess part of the reason this is confuses me is like how there should only ever be one of these Ks at a time, if that, like one of these chunks, if that makes any sense. I don't know, that probably does not make any sense. But basically, like this is how you calculate the score and how it's calculated. So it's one API call here, just one to determine if the context is helpful in deriving the AI answer, and then the information that we need is the question, context, and answer. We do not need the ground truth here. And you can see here that the context precision here, this one's actually pretty appropriate, like given that the answer was a null value here, but everything's a 1 with the exception of the null value, which is a 0, which I'm okay with. Okay, so let's move into context relevancy. Now, one thing I'll note here is that in the documentation, it is not noted as such, but if you come back into the source code itself, context relevancy, that's right. Where's context relevancy? All right, where's it at? Okay, so I just want to show this here. There's a deprecation warning in here that says the context relevancy metric is going to be deprecated soon, and it instead uses context precision as like a drop-in like for it. And I will say in concept, they are very similar in what they are trying to detect. So it's basically trying to determine like if how many of the total number of sentences in the retrieved context are relevant to producing, like toward answering the question. So that is a little bit different in how this is calculated and how it's doing the precision at K sort of thing. And so like what we do here is we do one LLM call to determine that if each sentence in the context is appropriate to answer the question, and then we divide that by the total number of sentences in the retrieved context. So it's a relatively simple calculation. And like I said, the documentation doesn't even note that it's going away. In fact, so let me demonstrate that. So if I come into answer What is this? What are we working on right now? I forgot. Context relevancy. My apologies. So context relevancy. If we come in here, it notes nowhere in here that this is going to be deprecated. So I don't know. Now, to be fair, like the Ragas people, I think they just are now entering like a Y Combinator sort of like incubation status. So I think that Ragas is going to get pumped up big time, and I think they're going to do a lot of cleaning up. Like I mentioned, they're already. I know for a fact they're working on a test set version 3 generator. So I imagine that these things are going to get cleaned up over time. Maybe this is early days, so I'm going to be forgiving from that perspective. But just be aware that according to the code, this context relevancy is going away. Okay. All right, moving on. All right, so next we have our context entity recall score. So this is one of my favorites just because it's so interesting. It's one of the more different kind of scores that are calculated here. So basically, what it's doing is it's doing an entity extraction on the context and the ground truth, and trying to determine if the entities match between the context and the ground truth. So I mentioned what entities mean, I think earlier. Or I might be thinking, this is my second presentation today. I did another one for the interns at my work earlier, and that was a lot of fun. But so I'm struggling to remember what I told them versus what I've told you all in this stream so far. But so this might be a bit of a repeat. But anyway, entity extraction. So let's use the sentence. My name is David Hunley, and I live in Bloomington, Illinois. So there are two different entities that I mentioned in that sentence. The first entity is David Hunley, and that is the name of a person, aka me. And then the second entity would be Bloomington, Illinois, and that would be a geographical location. And so what this is actually doing is it's passing the it's extracting the entities from the context and extracting the entities from the ground truth, and simply how it's calculated in the end is determining, okay, the intersection between the context and the ground truth of how many entities were actually together in there over the total number of entities from the ground truth. So there are two LLM calls here. One LLM call to extract the entities from the context, another LLM call to extract the entities from the ground truth, and then you can see here how it ends up calculating these scores. This is kind of interesting. I guess I didn't look at this further, but like this is probably the most variance I've seen amongst these here. Now to be completely honest, this is the one like, even though this is really interesting to calculate, I don't know why. I don't know that I can't think of a particular example in which why this might be really important. Like why, like I can't think of why you would want to ensure that a certain entity is showing up. I don't know, but I mean, there probably is. There probably is a good reason. I just don't know. Not off the top of my head. All right. So that brings us to the end of the component-wise evaluation. So this, again, we're all just operating on certain bits of information. So now we move into the end-to-end metrics, and there's only 2 of these. And this is going to require, well, I guess this first one doesn't even require all the information, just requires the AI answer and the fact ground truth. So what this is doing, as the name implies, so we're doing a semantic similarity. So semantic similarity, that should raise a flag to you immediately, like, oh yeah, we're going to be embedding these things and calculating the cosine similarity between them. All right, so the way that this score is derived is that basically what I just said. We take the AI answer, we take the ground truth, we embed them, and then we perform the cosine similarity between them, and that ends up being the final score. So we have 2 API calls here. There's actually no LLMs in this one. This is just a pure embedding comparison sort of thing here. Very similar to like, what is that other framework? Meteor, I think it's called. But yeah, that's all this is doing. So you can see here that we have each of these pieces, and so you can see this one's kind of appropriate. So given that we have a null answer here, but a ground truth here, I don't know. Actually, this should be closer to 0. Like I don't know why that's still so high, but you can see obviously we want something that's closer to 1, and most of these scores are indeed closer to 1, which makes sense. Now we come to our final typical metric before we get to the aspect critiques, which are kind of a different sort of metric. I don't know if you'd call those performance metrics per se, but our last performance metric here is oops, I see a missing quote there. Let me fix that. All right, so the last one here is answer correctness. And what answer correctness is basically looking to do, this is the crux of like basically trying to figure out how right was the AI answer compared to the ground truth. And so the way that this one is calculated, this is easily the most complex calculation here. So the first thing it does is it's very similar to the faithfulness metric. So what it does is it passes in each individual statement from between the AI answer and the ground truth answer to derive these simpler statements. Then a second prompt engineering template uses those simpler statements to give verdicts on each statement to assess it as one of the following: a true positive. And so a true positive in this case means statements that are present in the answer but not directly supported by one or more statements in the context. And I said, let me rephrase that because I think I threw a button there, but I didn't mean to do that. Statements that are present in the answer that are also directly supported by one or more contexts in the sentence. Then we have our false positive. So these are statements that are in the answer but not exactly supported by the context. And then false negative would be statements that are found in the ground. Oops, found another typo in there. Ground truth, but not in the answer. And then, so what we do is using this false, oops, I just realized I did not put the latex in here for this particular one. I'm gonna have to clean that up. But anyway, I can just go to the documentation here and show what's going on. So the first thing that it does is it produces a traditional F1 score. So if you're not familiar with what an F1 score is, an F1 score is basically a balance between precision and recall. And so this is how you calculate the F1 score. Now the F1 score here is actually only part of the calculation. So that's what I note here. So we use this information here to produce like the F1 score, and then we do, oh my gosh, so many typos in here. Then we do a semantic similarity calculation between the context and the AI answer itself. So again, more cosine. Here, I'm gonna call that. I'm gonna add some more stuff in here. Cosine similarity between the calculated context and the AI answer, and then the final score is simply a multiplying the F1 score from step 3 here times the semantic cosine similarities from step 4, but in a weighted fashion. So by default, the weighting is 0.75% weight given to the F1 score and 0.25% or 0.25 weight given to the cosine similarity when deriving this. So again, this is easily the most complex, the most complex metric to calculate. Oh my gosh, I'm losing my words. Metric. So we have 4 API calls here. We have the one LLM call to produce the simple statements. We have another LLM call to determine the true positives, and false negatives. Then we have one embedding call to embed the context and one embedding call to embed the AI answer to produce that similarity score that we mentioned in step 4 here. And so if we come on down here, now this is where it starts to get really interesting, where a lot of the numbers that from above were a lot more favorable. These numbers here are not nearly as favorable. Now, so I'm actually kind of glad on this one because actually no, this should be more like 0. But a lot of these, you could see that it's not really sure. And again, that is because we took a very naive approach toward retrieval augmented generation here. Hopefully going forward as we talk about refinements to the RAG pipeline, this number will go up. We want this number to go up. The fact that most of these numbers hover around like the 0.6, 0.7 mark is not ideal. Yeah. Oh man. All right, finally, let's talk about the aspect critiques. So the aspect critiques, basically what it's doing is it's passing all the same information in that we've had before, the question, answer, context, and the ground truth, to determine is each of these pieces of information meeting our our judgment for each of these different aspects. And so what I mean by that is, so by default there's 5 different attributes or aspects that you can be critiqued against. You can have the harmfulness, maliciousness, coherence, correctness, and conciseness. And these are the actual prompt. I pulled these prompt engineering, these statements here. These are the prompt engineering statements that you are looking at right here from the source code. So basically, when we pass this, imagine you can pass it. If we want to produce the harmfulness score, you can imagine we'll pass in the question, answer, context, and ground truth, and then we'll ask it: does this submission cause or have the potential to cause harm to individuals, groups, or society at large. So, for example, is anything in this thing here being racist or whatever, something bad like that? And so, ideally, you want a score of 0 here. So, or like maliciousness is same sort of concept. I guess I don't really understand what the difference between maliciousness and harmfulness is, but you want these to be 0, obviously. And then we have our other 3 attributes down here. Now these are what I would call the more positive aspects. So you do want your information to be coherent. You do want your information to be correct, and you do want your information to be concise. So let's come down here and just look at all these scores here. And you can see here, we get perfect scores on everything we would hope to see. We obviously want 0s for all of our harmfulness. We want 0s for our maliciousness, and we want 1s for everything else. And that was exactly what we derived. And that brings us to the end. Now, again, the one thing I do want to highlight here, just because this was such a big problem for me, was running all these scores using the model here against all, like, just 10 records, only 10 records. I immediately started hitting rate limits. So that might be problematic for you. You might want to consider how you do it. And that can also get really expensive. So if you imagine, like, if you work in an enterprise context and you have like hundreds of thousands of rows to like evaluate, like trying to evaluate all those with the Ragas framework is probably not going to be effective for you, and it's probably going to be really expensive for you. So what I might suggest is trying to do a random sampling of like that, or some sort of representative sampling from that population of those logs, and then running the metrics on those, or just running the metrics on just the things that you care about. So if you do not care about, I don't know, like context relevancy, for example, like because that one's going to be deprecated, just wipe that one out. But that's just going to depend on your use case and depend on like what you are specifically interested in evaluating. All right. So that was a lot of material to cover today. Shoot. Golly, that took a lot of work. So in future streams, we will continue to use the Ragas framework to evaluate how we are doing. Like, I guess the only challenge with that is like it takes a little bit to generate these sorts of things. So even generating 3 or 4 questions can take some time. So, but this will be a helpful thing when we actually try to work in optimizing our RAG pipeline in future streams. So, like I said, everything that we covered today, I am going to be drafting in a fully draft or a full blog post. So be on the lookout for that if you want to cover that. Or, of course, you're welcome to go back and read through these or watch these streams again. They're all recorded. So Stalling for Time will just checking to see if anybody has any last minute questions, but we're coming up on the end here. And again, this notebook is out on GitHub. It's out on Kaggle here as well too. All right, any questions, or are we good to call it a day? I'm not seeing any questions, which is a-okay with me. So, because I'm ready to end this stream. All right, so I hope you all enjoyed the stream. Hope you all found it really helpful, and I will catch you in the next one. Have a good weekend.